We are now going to speak about a concept that is called transfer function. And transfer functions look at relationships between input and output variables. So what does this mean? Means we have the idea of a system or a process, and this process has inputs and outputs. We call the inputs usually U of S and the outputs Y of S. And they are related through this block, and we call the dynamics that are contained in this block the transfer function G of S equals to the output over the input. So this is called let's put the arrow here, this is called a transfer function. So if you want to remember it, there's a cartoon by Brian Douglas, and what he said, he shows this person who is on the phone and speaks, "Can I please speak to a vet? Because I accidentally Laplace transformed my cat." So in the background, you see the following picture. See this little thing here, I hope you can recognize it. Divided by this picture here. So this obviously means that this, and then there's a little bubble saying here, meow. And this is the Laplace transform of a cat. The input is the cat food and the output is the poo. So this is a good way of remembering. It's the input inverse to the output. All right. So this makes more sense if we're looking at particular processes. So you may remember that we had the process where we looked at the concentration C1 of S, and that was defined as 1 over 2S plus 1 times Ci of S in our previous video. And now we can say that the transfer function, let's call it G1 of S, is therefore 1 divided by 2S plus 1. Because this is the output, C1 of S, divided by the input, Ci of S. And we can see the dynamic behavior based on this transfer function, and we're going to get more experienced as we look at more examples, what it actually means having those particular functions. We know that this is a first order system which has a response to unit step input that looks something like that. So if we change the input, the output will change accordingly. So now let's look at another example. This is in the textbook. It's example 4.2. It's the electrically heated stirred tank. So the process schematic for this looks like as follows. We have an inflow Ti into a container that has a certain level. We have a constant volume or hold up because we have an overflow line. We apply some heat, Q. We have a temperature and we have a stirrer in here because we want our temperature in the tank to be the same as our output temperature. So in the previous section 2 and 3, some equations were derived that describe this example. And this is M times C, where C is the heat capacity, M is the mass in the tank, dt over dt, so the temperature over time. So this is the rate of change of temperature is equal to the flow rate times the heat capacity times the input minus the output or the temperature in the tank. And now we're getting electrically added heat, and that is the temperature of the coils minus the temperature of the surface of the coils, which is the temperature in the tank. And we have another equation which describes the dynamic behavior for the heat transfer between the heating coil and the power that has been added, and that is equals to Q minus HE times AE. So this is the heat capacitor, and this is the area that is exchanged here for the electric coil. And again, we have here TE minus T. So that's the heat that's put into the system minus the heat that's getting taken out of the system, and it changes. That's the differential change of the temperature of the electric coil. So now we would like to think about transfer functions, and for this we can draw our block diagram of our tank, of our heated tank. And what are the input variables? Well, the input variables are the temperature of the flow into the tank, so we can change that. And what else? The heat that we put into through the heating coil, the electrically heated coil, into the tank. And the output variables are twofold. So it's the temperature in the tank, and it's also the temperature of the heating element. So now we have to put all the inputs. So these are the inputs, and these are the outputs. So in those two equations here, we have to put the inputs onto one side and the output onto the other sides. So that means for the first equation, we get M times C, temperature over time, is the output. But we have two more elements for the output. We have plus WC, this comes from here. And we have another temperature here. So we have plus HE times AE times the temperature. And then the outputs on the other side are WC times the inflow. And now we have, this is not really our this is also an output temperature. So we have here HE times AE times TE. We're not going to let it stand like this. So for now, we're putting this our second output variable, we're leaving it on the right-hand side. For the second equation, we have ME times CE dTE over dt. And we find another TE over here, so it's minus AE on the right-hand side, so this becomes a plus times TE. Equals to Q minus times minus the temperature equals to plus HE times AE. So this is here in the first equation, T is our input variable. In the second equation, we've got TE, which is also sort of our output, so our output variable on the other side. So now the next thing is we can do the Laplace transform of those two equations. And by now we should be quite comfortable doing this because we know that the Laplace transform of a derivative is S times the Laplace transform. I do have capital letters for my temperature, so I'm going to stick to them. So you're not going to notice that this is Laplace transformed only by the fact that we suddenly have an S there and not a differential. So this is going to change to M times C times S times T plus W times C plus HE times T. It's T of S because we're in the Laplace domain, equals to WC times TI plus HE times TE. And here we have MECE times S times TE plus HE times TE equals to Q plus HE. Sorry, there's a T missing here. Here we go. All right, so now we have to decide, do we want to model that means do we want to predict and figure out what's happening to the temperature T in the tank, or TE as the temperature at the element over here. And generally we would like to know what T is. So we're going to solve those two equations, equation 1 and equation 2, which have two variables in there. Through T and TE, we're going to eliminate TE. So we're going to take equation number 2, and we get TE is equal to, let's write this different, just do one step at a time. We're going to factor out TE, so we are left with MECE times S plus HEAE, and then factor out the TE, equals to Q plus HEAE times T. So now we can divide by everything divided by that is in front of TE, so divided by MECES plus HEAE. This way we're getting TE, an expression for TE, and that is that TE equals to Q plus HEAE times T divided by MECES plus HEAE. So please note that the most important information about the differential, or about the dynamics, sorry, not the differential, about the dynamics, is in anything that comes with an S. So that's in our differential. So our dynamics are captured with the differentials. And this we have here in equation number 1, we had also one S over here. And this is what we're looking out for, because this will define our dynamics. Okay, so we can take this equation, this is equation number 2, and stick equation number 2 into equation number 1. So we end up with one individual equation, and this one is going to be getting longer. It's M times C, S times the temperature. So we're going to factor the temperature out. So we still have an S in here, plus WC plus HEAE equals to WCTI. And now we have the additional factor HEAE times TE. So now we have to stick in our HEAE divided by MECES plus HEAE times Q plus HEAE T. Okay, so I've taken, to show you what I did. I've taken, this comes from over here. And then this guy here comes from the denominator. And then we have this here. This factor comes from up here. Okay, so we stuck this on up here in there. So let's continue. Now we notice we got another, by doing this transformation, we got another factor of T in there. So this we have to put to the other side. And what we probably should first do is we multiply with the denominator over here, which is MECES plus HEAE. So we end up with MCS plus WC plus HEAE times this bracket here now, MECES plus HEAE. And now we multiply this by T. And on the right-hand side, we have to do the same. So we have to do MECES plus HEAE, WCTI. And now we've gotten rid of the denominator. So here it's only HEAE Q plus HEAE T. All right, so we have to sort again. First of all, we have to factor out this bracket here to multiply the two brackets here. So we're left with M times ME, C times CE, S square. And we're factoring out for the different S's. So now we have an S square here. Okay, so let's see how many factors of S we have. We've got an MCS here. So this is, if we multiply this M times C with HE times AE, we get another part with S. So it's MC plus HEAE. Now plus this part here, this section here, we can also multiply with MECES, and that gives us WC plus HEAE times MECE. And now this all has the factor S in there, plus everything that doesn't have an S, and that is WC plus HEAE times HEAE. Okay, and now we have to put a big bracket around this times T. And now we also get another T from the other side. So I shouldn't have drawn my bracket there just yet, because now we also have minus HE square AE square. This comes from the right-hand side times T. And then on the right-hand side, we've got left everything that is to do with TI and everything that's got to do with Q. So we have we're left with MECE times S plus HEAE WC times TI and plus HEAE times Q. And let's just mark this with pink again. So we have an S square here. We've got an S here. We have no S to the 0, this equation here. And then we have an S over there on the right-hand side of the equation. Okay, this all becoming very cumbersome. So let's try and get some simplification here. So what do we end up with? We end up in the equation in the following format: A2 times S square plus A1 times S plus A0 times T is equal to B1 times S plus B0 times TI plus, let's call this is making index 1 here, indicating it's for TI, plus B02 times Q. So now we could write down all the parameters, and maybe the most interesting one is here, which simplifies, because this one actually ends up being this A0. A0 is the only one that simplifies to WCHEAE. Okay, and then for A1 we have WC plus HE AE times ME CE, and for A2 we have M times ME C times C. Okay. All right, so this is our model for our process, and the important bit is to think about that we have now two inputs. So we have our process, we have T as the output, and we have two possible inputs, and the one input is Ti, and the other input is Q. So what we would like to do is now to see the two separately, and we call this G1 of S. This is the first transfer function and the second transfer function. And the first transfer function assumes that Q equals to 0. And the second, so the input number 2 is 0. And the second one assumes that Ti is equals to 0. So that input is 0. And remember, it doesn't have to be 0. It just means it's static. That means it's steady state. It's just there's no dynamics on it. So this means that the transfer function for the first model here is B11 times S plus B01 over A2S square plus A1S plus A0 is equal to T divided by Ti, and this we call G1 of S. And the second function is that it's B02. I should do little brackets here so it's a bit clearer that this is not to the square. It's just an index that's running. B02 divided by A2S square plus A1S plus A0. And this is T when the input is Q, and this is the dynamic behavior that we quantify in transfer function G2. So now it's important to observe that this is a second order equation. As I said, we're looking how many S's do we have here. So we have an S squared and an S to the 0. So S to the 2, S to the 1, S to the 0 in both instances. So these are both two order processes, but this transfer function has a slightly more complicated dynamic because it has the term of S in here as well. So in the next video, I'm going to show you what we can do with these transfer functions and how we can play with them around, how we can put them together, because this is quite useful to have, splitting them up this way, and then we can add them up later. We can add up the result as the sum of both of these inputs, and we'll see in a moment how we're going to do that. And in the meantime, if you want to look at another example, you can do example 4.1 in the textbook and work through that, which is also explained in much detail, because we obviously get other examples of other transfer functions. It seems very difficult and cumbersome what we just did. So this is, if we're looking back here, so these are some equations that we started off with to describe the process model of the heated tank. But at the end of the day, we're only looking at the format of the final transfer function, and we see the structure is S to the square. So it's B1S plus B0 divided by A2S to the S square plus A1S plus A0. And this is going to be a repetitive function that we have. And this is a second order process. So we're going to see first order processes. and second order processes and integrating processes. So we're not really seeing a huge variety. And this format, even though it looks cumbersome, is something that we're going to encounter again and again and again. So don't worry if it looks complicated to begin with. We usually try and make the coefficients A2, A1, and A0, put them into numbers or parameters as soon as possible, so we don't have to carry all these long equations like this one here with us for a long time. All right. So in the next video, I'm going to talk to you about properties of the transfer functions and something that we call the final value theorem.